Well, dear, welcome back. So, we are continuing our discussion on how to mathematically model a humanoid robot, and in that context, we have taken an example right now as Baxter. Okay, and in my last video, at the end, I told that Baxter is an industrial robot. It's a, I think, if I, in writing I am making some mistake, if, you are calling it a typographical error, maybe this is phonographical error. Baxter is not actually meant for to act as an industrial robot the way we mean industrial robot, means with high precision and danger to the human life, okay, not collaborative. Whatever you perfectly program, it will do only that job. So in that context, Baxter is not really an industrial robot. It's a cobot, collaborative robot. Okay, and today we are going to tell you how to move forward to make a forward pose model for Baxter left hand, and for right hand also there will be similar kind of approach will be similar. Okay, and you know we have in my earlier lecture from DH table. So this is your DH table, which, like other industrial robot you have made, the moment the robot is given to you, once you made it correctly, then you see that using this table we have generated all kind of individual matrices, right, of the left hand, and by just connecting them together, that is, connection means multiplication, and that is the transformation, matrix multiplication in order, we can get the mathematical model of Baxter robot the way we have done for industrial robot as well. But I would like you to note it down here that since it has a redundant joint, extra joint, to have enough dexterity, so its expression for the forward kinematic equations will be much more complicated, and eventually dynamic equation will be much more clumsy, means complicated. So that's a challenge, how to make them compact as far as possible, uh, um, as well as capture the real robot essence. Okay. So, having obtained these matrices as a raw material, we are moving forward to make a progress in developing forward pose estimation solution for Baxter type robot. Okay. So, and in doing so, actually in earlier, we substituted cos theta I equals to c theta I and sin theta I equal to s theta I, okay, as an abbreviation of cos theta and sin theta. But in developing further grouping among the matrices, grouping means again matrix multiplication, to make more cleaner expression, will actually make further substitution. Cos theta I equals to simple Ci. We are eliminating theta, and sin theta I equals to Si. But everything is there. Okay, Si means sin theta I. That means sin theta 1, theta 2, theta 3, depending on the value of I. Okay. So now you see, for any robot, if you are trying to make a mathematical model, anatomically you will have to study the robot, its construction, right? So here also we do the same. So these are my raw materials which we have already, and we have just for model development, to avoid unnecessary computation, we have ignored this constant terms, right? 0 with respect to left base, or 0 with respect to right base, then gripper, left gripper with respect to end joint, which is 7, joint number 7, all these expressions we have kept handy so that when finally it will be done, our modeling will be done, we will just multiply them with those matrices because they are constant matrix. There is no variable in those matrices. Okay. Now look here carefully. What we are trying to do here, divide and conquer. I am calling it divide and conquer. It's a algorithmic term. You see, here we are looking to the solar joint. Right? So there are 2 degrees of freedom in the solar joint. So we are trying to get transformation matrix of link 2, theta 1 and theta 2. These are the 2 joints, 2 motion, you know. Again, try to recapitulate. Shoulder has roll, which is theta 1, and pitch, theta 2. We are calling theta 2 as pitch. So, I am now making a shoulder transformation matrix. Okay? So, this is what we are actually trying to do. So, segregate. These are the 2. This is my shoulder joint. Okay, theta 1, theta 2. So theta 1 and theta 2. So this is now if I multiply these 2 matrices, okay, that theta 0, 1, which is a function of theta 1, and then theta 1 and 2, which is a function of theta 2, will give you this matrix. Okay, and since you see the matrices are such, thanks to our coordinate axis selection, you see at least first and last the way we have selected, many zeros and ones are there. So this is multiplying these 2 matrices, this one and this one, really is not very tough. Okay, so you can actually easily do that, and that is resulting equation number 1. Okay, then you look elbow. So this is my elbow. There are 2 joints also. Elbow roll and elbow pitch. So Z3, about Z3 is the roll, about Z4 is the pitch. So again elbow, we are trying to create a elbow with respect to elbow joint, that is with respect to 2, that is with respect to 2. Transformation matrix of 4 with respect to 2. So we are taking this one and this one. We are clubbing them together. So these 2 we clubbed to get 2 with respect to 0. This we are clubbing to get 4 with respect to 2. So this is divide and conquer. This matrix multiplication is also doable because you are just multiplying this one and this one. And we have got equation number 2. And then we are coming to the wrist where we have 3 joint axes. Okay, Z5, Z6, Z7. Clear? Okay. And you see about Z5, as usual it is roll. We are just defining. About Z6 it is pitch. About Z7 again it is roll. That is the way we are defining because that's a convention. Okay. Actually, all rotations are taking place with this about Z axis. Okay. Clockwise or anti-clockwise. Okay. So this is now wrist. So remaining matrices, if we multiply, okay, 5 with respect to 4, 6. So if we multiply to get, you see, 5 with respect to 4, then 5 with respect to 6, and then 6 with respect to 7, then this matrix will represent our wrist. Clear? Because wrist has 3 joints, okay, and we are multiplying them, and then it will be a function of, that is exactly what we have done here. So it's a function of, remember, each individual matrix is a function of one variable. Okay, so that you must remember always, and that's the way we have to avoid simplicity. We have made at least initial raw materials have simplicity. Okay, so you got wrist, you got elbow, you got shoulder. Now having got all this, and let us call it equation number 3. And now having all this, we are trying to create um, elbow, transformation of elbow means anything if I know with respect to elbow joint, I'll be able to straightway know with respect to shoulder joint by multiplying that anything. Anything means some position vector, okay, which will be 4 cross 1, say for example, and then if we multiply with this, so we will get what? We will get a vector which will be with respect to shoulder joint. Okay, so that's as simple as this. So that's why we are now computing the important matrices. So elbow with respect to shoulder. What you will have to do again, matrix multiplication, you will have to multiply two matrices 1 and 2, okay, in this order, okay, in this order, so that you get transformation matrix of 4 with respect to 0. 4 represents actually your elbow, and 0 represent with respect to 0 is shoulder, okay. So you get the transformation matrix for elbow with respect to shoulder. This is very important matrix, and we are actually will be using this matrix again afterwards also, and this matrix also we will be using. So we are calling this, I am calling this matrix as B, matrix B, and these are the elements, okay. Somehow I have, you have with your notebook and pen, once you have done this 3 multiplications, right? Now let us simplify it by notation. This is a matrix B, so I am calling it B11. That means this element is first row, first column. B12, first row, second column. This element is first row, third column. This element is first row, fourth column. So B11, B12, B13, B14 can be substituted in place of these expressions respectively. Similar is the case S6, C7, B21, where actually then B22, B23, B34. Okay, so all this substitution we are making. So this will be now a matrix like B11, B12, B13, B14, like that. B21, B22, B23, and B21, B22, B23, and B24, like that. Okay. B31, B32, B33, B34. Okay. So B41, B42, as simple as this, 43, and B44. So this is our matrix B, which we are defining. Okay, and all these elements are these elements. Okay. Now, continue our discussion. Now we need to calculate elbow with respect to shoulder. That means this matrix, transformation matrix of 4 with respect to 0. Okay, with respect to 0. Transformation matrix of that means this and this we are multiplying to calculate elbow with respect to shoulder. Okay, and this is the matrix, and I am calling this matrix A matrix. Okay, and similar is the case. Just once you have by pen and paper, once you have done at least this much is doable, then quickly we are actually making a substitution. Very simple. A11, A12, A13, A14, like that. So this matrix, these are the elements of this matrix. And why we are doing that? We are doing that because assuming that further, that means ultimately we will have to calculate this one, right? Transformation matrix of 7 with respect to 0. Okay, that means wrist with respect to the base or the shoulder. Okay, so in doing so, we will have to do this. Clear? And doing this, you can imagine multiplying this matrix uh, by this matrix really cumbersome. We won't do that, and you will also perhaps will not do that. Octave we have, thanks to symbolic computation tool, is a open source, so you can use Octave's symbolic computation tool, where you need to only define these matrices. What is A11, A12, A13, A14, B11, B12, like that. Okay, all the A and B matrices you will have to define with respect to the actual sine cosine expression which we have. Now, once you have defined that, then you can multiply. You can use the symbolic computation tools matrix multiplication technique. So what you are trying to do here is, this is a 4 cross 4 matrix, this is a 4 cross 4 matrix. Okay, so you just do this and you will get another matrix, which is our in this case this. Okay, and this will be another 4 cross 4 matrix, and your work will be done. So you don't have to do the symbolic computation tool of Octave, or MATLAB also has, but MATLAB is proprietary. If you have an access to MATLAB, go ahead and use it. It's very simple. So that's why I have shown here that how you could crank out in a simple way by proper substitution these computations. More elaborately, I am just showing this here. You see, this is what I have, right? This is so this is what, this is the pose. This is inside pose. What you have sorry about that. So yeah, so inside the pose, this is the pose, right, where you have 3 cross 3 orientation, and this is a translation. That is the end effectors position and orientation, or pose. And how you are getting that? You are trying to correlate that by multiplying two matrices A and B, and then what will be the element? Now we will directly using symbolic computation tool you will be able to do. This is simple matrix multiplication. So what will be the R11? This is all 4 cross 4 matrices. R11 will be multiply this elements, this row with this column, right? This is what matrix multiplication. So A11 into B11 plus A12 into B21, A13 plus A13 into B31 plus, there will be a plus A14 into, you see, 0. That's why I am not writing it here. Okay, there is AI4 also. Okay. So that's the way, you know, you got R11. Similarly, R12 will be R12, right? Like that, you get it. Okay. So A11, B12, A1 plus A11, B22 plus A13, B32 plus A14 into 0. Okay. Right. And likewise, you'll have to do this. You'll have to do this to get R11, R12. That means first row is completed. First row, first element this, first row, second element this, first row, third element is this, and then first row, fourth element, you see. Now, since this is 1, so A4 into 1, okay. So that will be there. This is B44, okay. So that's the beauty, because we have 1, 0, so this becoming a little bit simpler. So same thing now, you want to get, so first row is obtained, now second row, second row in a similar fashion, you got like this, okay. It's a good idea actually to do this in a symbolic way, because you will have to define A matrix, B matrix, and this matrix multiplication, which is very simple, I understand, but still you can do of your own um, to check these results, okay. And then we have also, you see, R31, R32, R33, and Z. So all these 9 elements, 1, 2, 3, 4, 12 elements, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. All these 12 elements, this 4, 4, 4. Total 12 elements are obtained, okay, by matrix multiplication. And then you can just correlate. You have got the forward kinematics solution, because you see now all the terms, I have written it, I have shown it here, but this again for your convenience, please check. All the terms you will have to write once. You will have to write this only, and then multiply, and you will get all this in terms of sine, cosine, theta 1, theta 2, theta 3, theta 4, theta 5, theta 6, theta 7, all, okay? But this much you will have to do. So, where all the matrix elements in terms of joint angles are shown here, okay? So, you see, using divide and conquer, just studying the anatomy of the given robot, okay? So, this is the strategy everywhere you should follow. You could easily get the forward pose estimation solution. Okay. That means the final pose of the vector, left hand or right hand, whatever it is, has been captured as a function of joint angles. It is forward because if you define joint angles, okay, then that means I am rotating the joint motors 1 to 7, right? And manipulator will move somewhere, and that pose is actually, this is the pose when you are all giving these angles. So this is, as you know, called forward pose estimation model. Now what can we do with this forward pose model? Nothing much. We can simulate, okay, in a graphical way. If you have a robot model, use computer graphics. You can give theta 1, theta 2, theta 3, theta 7, and it will move from here. Okay. Then what else you can do? You can design game where the robots will be moving, and so the way you want robot to move, you define joint angles accordingly, and you can use these equations. Okay. You can use these substitutions and this equation, this equation, this equation, this equation. This is forward kinematic equation to get all these things done. And one more thing you can do, you see, working envelope. You can figure out working envelope. Only thing is here, you see, you have now, you can run loops, okay, theta 3, theta 5, theta 4, theta 3, theta 2, theta 1. And since all this, so theta 1, theta mean, theta max, ranges are given, so you can compute a nested for loop, okay, so that for a particular theta 7, for a particular theta 6, for a particular theta 5, all kind of thing, you just get all the points where and use these equations, right? These forward kinematic equations, expressions to run those loops, and eventually you will get all these values, and you capture them, and if you using graphics, if you know how to do that, and then you will be able to figure out the working envelope of this type of robot. Okay. So these are the things which actually you can do using forward kinematics. This is very important. Modeling, first modeling is your forward kinematics or forward pose estimation model. One more thing you can do, you can just in a teach pendant mode by pick and place, you can do means you bring the robot somewhere, okay, and all the joint angles is memorized, and then next time you keep some object where the robot gripper where, okay, in a open gripper configuration, then what will happen? Just you will have to add close gripper. So put some object there. Because the joint angle has been memorized, the pose will be visited again and again by the robot controller, the computer here, high level controller, and adding close and open gripper, you can just pick, and where you need to place, you can place. So you don't require very complicated things in doing so. But wait a minute, there is no free lunch. Means this forward kinematics is not at all complete modeling, because many informations are not there. One, the fundamental information, if I want a robot to follow a trajectory, okay, with forward kinematics, it will not be able to do unless you use stitch pendant mode. Well, industry people use it, okay, it's very easy, but actually as a roboticist, you should know how robot can follow the trajectory. For that, you need to solve inverse kinematics. And since the challenges here are, and in most of the humanoid robot, since actually most of the humanoid robots, they are aesthetically like human hand or something like that. So they do not follow Piper's recommendation. And if they do not follow Piper's recommendation, then closed form inverse kinematic solution is not possible. So we'll start from here in the next class, and I will show you that how the inverse kinematics solution can be made. Okay? Okay? Till then, bye-bye. Stay safe. Have a nice day.